Okay.
Okay. Turn this into a show. There we go. Now you can see my pointer. Is that correct? This pointer moving around.
Yeah, we can see that. Yeah.
Yeah,
Good.
see.
Okay. So this talk is about topology and particles, and it's um, although some of this has been thought about since long ago, very long ago. It's all in a sort of state of flux, as you'll see. Maybe the best diagram in the talk is the one you're looking at right now. I found this cartoon, and since it's sort of the end of winter here, I thought it was a nice one to put up. The idea of a Penrose triangle made out of snow is enjoyable somehow. Okay, so now I might remind you that there are charts like this that are worth staring at. That contain all this information about elementary particles. And I might remind you that it got down to the point of certain kinds of particles called quarks, which are not isolatable. They won't be seen all by themselves, but they form the composition for things like protons, and that the usual theory, the standard model for elementary particles, is laced up with group theory because of gauge theory and symmetry, and so associated to elementary particles are irreducible representations of unitary groups. So, for example, the quarks correspond to fundamental representations of SU3, the algebra. There's all this information, but it did get into a very, very clear crystallized pattern by the middle 60s with the work of Kauffman and others. But there is still this speculation that goes all the way back to Kelvin and the people who were drawing pictures around Kelvin, that maybe knots are somehow, or topology is somehow in back of what's going on with particles. Here's an ancient picture from the mystics, Besant and Ledbetter, of what they thought was an atom. Of course, this has no particular relationship to anyone's theory, but it's interesting that they would draw something as complex looking as this, partly influenced by Lord Kelvin and his idea of vortex atoms. And there were other people writing at the time. This is just a little historical digression. There were other people writing at the time who festooned these kind of pictures with many decorations. It would seem that Mr. Babbitt actually is the origin of this picture, which was simplified by Ledbetter and Besant. But a more modern example, what question?
Yeah, just an observation that they look quite a bit like knotted surfaces.
Oh, they do, don't they? That's right. If you were to look at it as a section of a knotted surface rather than a single knot in three space, and maybe from that point of view, you could attribute some visionary wisdom to these people. Yeah. And this is a more modern schema about something circular due to John Wheeler, who liked to indicate the epistemological problem of quantum mechanics, which he was fond of, by drawing a U, letter U, which is the universe, and the universe has an I, which is looking back at its origins, the Big Bang over there on the right. And then, according to quantum theory, a phenomenon is not an actual phenomenon until it is an observed phenomenon. And that would mean that the universe isn't actual until it somehow manages to observe itself. But it would seem that it had some actuality prior to that observation. And Wheeler liked to create some thoughts with this picture of his. A large-scale topological picture of the universe. But I want to wander for a little while through things about topology and quantum theory for a moment without getting to the elementary particles, and then we'll get to them. Here is a diagram for an entangled state, and the way I have drawn this, you'd best read the bottom line here. I see my pointer doesn't actually exist on this screen, so I'll only talk. The bottom line represents a state which is 0 tensor 1 plus 1 tensor 0 over root 2, and you can observe it. Let's say Alice observes it in the left half and Bob observes it in the right. And if Alice observes it, she could either see a 0 or a 1. But if she sees a 0, then that's coupled with a 1. And if she sees a 1, then that's coupled with a 0. And so what Bob will come to observe after Alice observes is fixed. And Bob and Alice can be separated in space. That's an entangled state. And so it's interesting to ask whether there is some perhaps topological connection between the two observers that corresponds to the entanglement. And where would such a topological connection be? And that's a different talk, but I wanted to talk about it a little bit just to bring in knots in another way, because Aravind, we'll skip that slide. Aravind likes this entangled state, the GHZ state, which consists of 3 factors rather than 2. And as you see, this has the same property. If anybody makes an observation, then the other 2 observations will be 0. Or if anybody observes a 0, then the other 2 will observe a 0. If anybody observes a 1, then the other 2 will observe a 1. And Aravind said, well, this is analogous to the Borromean rings, where if anyone makes an observation of the Borromean rings in the sense of grabbing one of the rings and removing it, then the other 2 are unentangled. And that's what happens here. When an observation is made, it goes to an unentangled state consisting of 0 tensor 0 or 1 tensor 1. So this state is a quantum analog of the Borromean rings, an interesting topological analogy. And so Aravind suggested, at least implicitly, that maybe entanglement could be thought of in terms of linking. And his model is a kind of mechanical model. You take the link and you snip one of its components that corresponds to observing in that tensor factor. And then you look at the entangled nature of the other 2 components. So you could have one where it's not the Borromean rings. Maybe red and blue are entangled with one another, linked like a hop link. And when you observe in green, you get an entangled state. Such things can happen, but even more complex things can happen. For example, here is a nice state, the second one in the third line there, the one in the third line called the Werner state. And you see the Werner state is 1 tensor 0, 0 plus 0 tensor 1, 0 tensor 0 plus 0, 0, 0 tensor 0 tensor 1. And if you were to observe it in the first factor, let's call that Alice, if you observe in Alice's direction, then you could get a 1 and you would have 0 tensor 0, and that's unentangled. But if you observed the 0, why then you would get 1 tensor 0 plus 0 tensor 1, the remaining parts, and that is entangled. So you see that depending on how you observe it, which direction in Hilbert space, which which choice actually becomes actualized. You could become entangled or not entangled. And that's not like snipping a link. If you snip a link, it's either linked, the remaining part is either linked or it's not linked. So this is a case for perhaps for quantum knots, which would be superpositions of knotted states. Then you could imagine something like this, that when you snip green, it also creates the possibility of one or the other of things happening at that crossing that green is pointing to. Either it leaves it alone or it switches the crossing, leaving you with red and blue entangled with one another. You could try something like that. Sam and I have often talked about this and not quite formalized how to deal with this entanglement observation Arvin thing using superpositions of knots and links. But it did lead us to think about superpositions of knots and links. So you could have a superposition of two different knot types, which when you observed it would yield one knot type or the other knot type. And in fact, we worked away at that and made it a little more quantum mechanical by having the knots, the quantum knots, represented by mosaic patterns, grid patterns, so that they were all tensored up from some basic data, these little mosaic tiles you see on line 2 in that slide. And then you could have a superposition of things like that. And then you can define unitary transformations on these knots represented as tensor products of elemental things. You can define unitary transformations on them that correspond to the Reidemeister moves. So the topology becomes quantum mechanical. And we're still playing around with that model. But as you see, in a way, the model began with this Arvin question, and that hasn't been, at least between us, hasn't been settled into a bit of theory yet. It would be interesting to see whether we could represent a lot of entangled states and their measurement structure by using the quantum knots. So that's a story about knots in relation to quantum structure. And an older story is this paper by Herbert Yalo, which I've often looked at, but don't understand very well. But he had a perfectly clear idea. His idea was that elementary particles would be quantized knotted flux, like quantized knotted electromagnetic flux. Very nice idea. And then for him, the neutrino was a trefoil knot, and the anti-neutrino was the mirror image of the trefoil knot. And as Scott was saying, there's something four-dimensional in here. You could imagine that your well-known scenario of a trefoil knot and a mirror image trefoil knot doing each other in by taking their connected sum and then bounding a disk in force space would have to do with the particle interactions. And it seems, if you look at Yale's paper, that he had something like that idea for his interactions. So he had lots of pictures, nicely drawn, of different kinds of interactions of quarks and neutrinos and all those things, but he didn't have any analytical mathematics behind it. So this early stringy kind of theory didn't go anywhere except a series of papers that he wrote. And other people write papers occasionally with a nice geometric idea about particles. And that's what we're going to be seeing in the rest of this talk. Things that haven't quite gone anywhere, but have an idea in them that's interesting to look at. Here is another viewpoint. We know that if you try to pull two quarks apart, then they form then the strong gluon field appears between them, and it is stringy in the sense that it has it's mostly along a linear dimension, a one dimension between them. And if you pull hard enough, in fact, the energy goes into the field so strongly that new particles appear in between, and you can't pull quarks apart because of that, but you can get long stringy entities of gluon field. So this is in back of what is presumed to happen when you have proton-proton collisions. Remember, protons are made of quarks. So two protons collide, and they really can collide in accelerator experiments. And what's spewed out are these long quark strings of quark-antiquark pairs, and they might knot while they're flying around. You might get a knotted string, and then the ends might come back together and annihilate, and you'd have a closed loop of gluon field. And those are called glue balls in theory. No one, of course, can directly observe such things. And you can wonder whether certain energy levels in the productions of proton-proton collisions, which physicists would label as glue balls, might be knots. And some people have wondered about this. I don't have the most recent papers on this looked at. This one is by Antti Niemi from a while back, Are Glue Balls Knotted Closed Strings? And this is one by Buini and Kephart, asking the same question. And they had a creative suggestion. They said, well, couldn't we compare the energy levels of the knots with the energy levels of the glue balls? Well, what are the energy levels of the knots? You'd have to choose something that you would call an energy level of a knot. But if you were to, next demo courtesy of Jason Cantarella, if you were to take a knot and allow it to contract to its least form, that is, it's trying to contract, but in his program, he allows the diameter to increase. So it's like a rope, and you're using the least amount of rope in order to make the knot. And you could take the length of that rope divided by the diameter and call that the energy level of the knot, the rope length. So you can do computer experiments like this and get charts of rope lengths, as Jason Cantarella has done. And then you could compare those rope lengths with the energy levels that are purportedly glue balls. And this was done, and they get a pretty good correlation between energy levels of knots coming from the tables in this sense and energy levels of the glue balls. And how far they've progressed on this recently, I don't know, but that's an example of hopefully getting at trying to peek around the corner at the possibility of something being knotted down in there. Okay. And now we get to a more theoretical idea. John Williamson has written some papers where he suggests that you could take the electromagnetic field, which kind of looks like a twisted ribbon in the form of its E and H parts, and wind it around itself into a closed loop, and that ought to be an electron or a photon. An interesting idea. Yeah, now in John's case, he has a lot of Clifford algebraic kind of mathematics surrounding all of this. But I think if you were to read his papers, you would find that the algebra of all that differential equations is working fine. And then there are qualitative ideas which take you over to these pictures, but there is no, it's not like he is going to derive an equation for this closed loop or anything. That's going to be some project for you or him in the future. So he's proceeding from certain theoretical ideas that he would like to put together, and some Clifford algebraic ideas as well. be that as it may, here's another one. I'm going through my little list here. This one is a very imaginative idea due to Jacques Evrin, which he published in the JKTR. And his idea is as follows. It's almost a pun. You see, if you were to take a Mobius band with 3 half twists, and flatten it like this, then you could look at it. And this flattened Mobius band with the 3 half twists comes in different categories. You see, as you go around, no, I don't have a pointer, but as you go around the upper left one, walking around it, you're walking along the surface and then you go down in the sense that you were above the place where the twist happened. And then you have to go up and then you have to go down again. So this consists of 2 downs and an up. And it consists of 3 things. So maybe this is a down, down, up quark. Maybe it is, right? Maybe you can think of it as something like that. Or I'm sorry, you can think of it as 3 quarks, 2 downs and 1 up. So you could think of it as a proton. So depending on the ups and the downs, there are different things that you could attribute to it. And so he starts with the topology of Mobius bands and uses them as diagrams for particles. Interesting idea. And then he can have particle interactions like this. His particle interactions are that you would take this guy, for example, as a neutron. What is it? It's a down, down, up, apparently going around that way. Anyway, you fold it over and you cut it. And it becomes 3 of them instead of 1 of them. And the 3 that you get correspond to the proton, the neutron, and the electron by watching the downs and the ups. And that's a valid particle interaction. Now, what I do not know about his model, although he did a lot of examples and they seem to work, what I don't know about his model is the extent to which all the interactions you might build this way are physical. I would imagine if one went through this carefully, one would find that some subset of them correspond to physical reactions and some other subset is just spurious. Of course, it would be much better if they all corresponded to physical reactions. And I don't think he ever did make a chart of all of that. And I keep meaning to go back and perhaps do that, but I never did. A good project for a student. Now, here's another one. This is not topological yet. This is the Rishon model from a while back by Chaim Harari. And in his model, which I have a better picture of the entities in it here from a different paper, the quarks have substructure. And there are these, I forgot what they're called. There are mnemonics, tau and vav, I think. Yeah, probably tau and vav for these constituents of the quarks. And then particle interactions are explained in terms of these subquark constituents, for which there probably is no group theory. This inspired Sundance, Bilson, Thompson to make a topological theory, which looks like this. So now you have triplets that correspond to fermions, including quarks. There's an up quark and a down quark and so on, and a neutrino and so on. They're each 3 braids, and they're framed 3 braids. So that's how to read these pictures. He could have put a twist on the band, but that's probably is a little too hard to draw. So these have pluses and minuses on them. They mount to 360-degree twists on the bands, and they're framed braids. and you can multiply braids together, and you can multiply the frame. When you do multiply them, the framings combine to give you new framings. So this is Sundance, Bilson, Thompson's modified version of the Rishon model. And he finds that he can let me skip that slide. He finds that he can represent some particle interactions by multiplying the braids together. So over here on the right, over here on the left, you have a muon in his classification. And over here on the right, you have the muon neutrino at the top, no charge. Those minuses have to do with charge. You have an electron neutrino, and you have an electron. This is actually the anti-electron neutrino. You see its mirror image, the one in the middle. And that's the particle interaction. The muon goes to a muon neutrino plus an electron plus an anti-electron neutrino. And if you multiply the three braids together, they unwind and produce the muon. So he suggests that the particle interactions could be products of braids. Now, I ended up having a collaboration with him for a little while, a long time ago. And part of it had to do with the fact that they had gone along from this idea to this idea, partly because they were being pushed into this idea by Lee Smolin. And the idea was that these braided elementary particles could be part of a larger surface network, right? So you imagine some surface, and you've localized a surface with boundary, and you've localized along the surface with boundary an electron neutrino over here, or somewhere over here an electron. And they would interact by the surfaces coming together and bumping into one another instead of just braiding. And it would be up to isotopy of those surfaces in three-dimensional space. So then the braiding interactions kind of disappeared. And it was at that point that I got involved in the conversation with them, and I'll explain to you what we did in a moment. But I realized on looking at it all over again more recently that there is a question, and maybe they came to doing it this way because of this question. I have to get back to them and ask. The question, oh, by the way, this nicely drawn picture and description over here on the right is from an article in the New Scientist. The theory it did get some publicity for a little while before it seems to have vanished into obscurity. But here's my question. And I'm explaining to you why I didn't ask this question immediately. It was because we weren't doing braiding. We were playing with surfaces. You'll see what we did. But if you go back to the braiding, there's a question you have to ask. Braids are an algebraic system, and it's not commutative. And if you say that this muon decays into these three products, three partial factors by factoring the braid, then what if you were to multiply them back in some other order? Because after all, usually you don't think of an order involved in the decay of a particle into some pieces. You don't think of that as ordered. So I could take those three and put them back together in a different order, like I did on the right over here. You can imagine multiplying that together, and you see the braid is longer and doesn't come apart. So should that also be the muon? Or does this theory fall apart because of the fact that braid multiplication is non-commutative and the particles should somehow be commutative with regard to their interactions? But then I realized on thinking about this slideshow, as I said, you're listening to something that was unfortunately by your lecturer neglected for too long. I had this question in mind, and then I remember again that we were dealing with the surfaces, and so maybe at the surface level, the kind of thing that we're factoring it by eliminates this problem, but there is a problem, So what did we do with the surfaces? I thought I would tell you a little bit. Oh, yes. And of course, before doing that, it's worth comparing these two ideas, right? Now, I haven't done the same particle interaction left and right, sorry, but one guy's idea was to manipulate a little topological entity and then cut it apart into pieces, let it undergo a certain kind of cobordism, perhaps. But the other guy's idea is that you factor something in a braid form. But they aren't unrelated. But on the other hand, how might they be related? Not obvious. Now, getting back to the surface idea. Well, if it's surfaces you're talking about, then you should be allowed to grab the head of that, like grab the top of that electron neutrino and twist it around, right? And that this is what we were thinking about. You should be allowed to twist it around and braid it through itself, and you'd get a different one, right? So we were concerned with getting different ones, that wasn't just the braiding. And that's what we were studying in this paper a long time ago. And you see, when you twist such things around, you get this kind of phenomenon. We're keeping the endpoints fixed here and twisting this. And if you grab the end of one of these closed things and twist it, you can put in one of those twists that I just showed you. It's an old story in making braided belts. You see, you can start with a bit of leather with a couple of slits in it, and you can make a nice braided belt out of it by braiding it through itself, and it twists. And if you do it the right number of times, all the local twisting goes away, and you get a braided belt. And you can keep doing this recursively, putting as much braiding as you like into your leather slit object, like that well-known idea. And the way you do it is you do the braiding that you want. You get some braiding below, and then you undo that, and you do it in such a way as to not have twisting on the strands themselves. So we incorporated that kind of belt trick into the equivalence relation and started thinking about what will happen to these gadgets if you allow that to happen to them. And they will change, of course, but on the other hand, we're looking at an isotopy of the boundary, and so we can keep track of how they change. And we tried making some charts to see what would happen to those particles under such an equivalence relation. But now, as I said, I have a different and maybe better formulated problem here, because I want to know what that does to the original braiding multiplications and decompositions. But this is all a little unfinished, and it has the feeling that it should have been more finished than this by now, but that's the way it is. So that's what some of this looks like. You see, you can take those particles and start twisting their surfaces around. So there's some topological persistence in particle properties for the surfaces, but to what extent do the surfaces represent elementary particles? To what extent could you make a theory of the elementary particles as coalescing out of some big surface network? We have no idea how to actually globalize and localize in that way. It's an interesting question. And now I get to another thing. This is a very intriguing paper by Joachim Lambeck, who may be known to you as a category theorist, but he was interested in physics as well, and language. He had a lot of interests. His paper is entitled Four-Vector Representation of Fundamental Particles, and I think it's a nice to carry a copy of the chart in this paper with you if you're thinking about elementary particles. I'll show you why. He said, I'm going to associate a four vector with each elementary particle. Since he was partial to the quaternions, he wrote his four vectors in the form of A plus BI plus CJ plus DK. But I, J, K, and 1 are just the four directions in the four space, and he isn't using any quaternion structure. I think he hoped to use some quaternion structure. So then the electron is this vector, 1 minus I minus J minus K. And the neutrino is just 1, and the red up quark is 1 plus J plus K, and so on, as you see here. And here are some anti-fermions on the bottom of the page. You have a chart for almost everybody. And here's a proton, which wasn't somehow on his chart, but he meant this. Neutron 3, proton 3 plus I plus J plus K. Well, here's the same chart. But on the right, I have written some particle decompositions. So we can do a little arithmetic in our head, and now you'll see how his chart gets used. Take the neutron, which is supposed to decay into a proton, an electron, and a neutrino. Well, 3. And the proton is 3 plus I plus J plus K. And the electron is 1 minus I minus J minus K. So if you add an electron to a proton, you will just get 3 plus 1. So you need a minus 1, and that's the new star. New being 1, new star is minus 1. You see, that's an identity. Everything I've written over here, these are various particle decompositions. A neutron is a red down quark plus a green up quark plus a blue down quark. Well, that's an identity about these vectors. There are lots of identities about these vectors, and each one apparently is a particle decomposition. Here, there doesn't seem to be any fuzz. Doesn't seem to be, at least. Every vector combination corresponds to a certain way of decomposing the particles. So if someone has told you a whole bunch of particle interactions and put them down, like I have put them down on the right-hand side of the screen, and you want to remember them, you can just keep his chart around, and then his chart has embodied in it all these particle interactions. Now, I think this is very interesting and mysterious. As I said, the usual theory of the particle interactions is that certain representations decompose into other irreducible representations under tensor products. So if you were to take tensor products of, well, never mind, that's the rule. But here, this is much simpler mathematics. This is just adding some vectors. And surely this is related somehow to that more group theoretic point of view, but I don't know how. I don't know whether anybody has studied this since he wrote it, which was when, back about 20 years ago. But in any case, this is a nice cheat sheet. And if you're trying to read about elementary particles and you feel like there's all this complexity of interactions and you would like something which contains them, then his little slide rule is a something which contains them. But his slide rule begs for a better theoretical explanation. And maybe someone here could supply that. Maybe we could figure that out. So this is the most focused problem I've presented you with today, I think. So that's his vector bookkeeper. And then there is another thing which, along these formal lines, I think is very interesting. If you were to look at the way physicists write down the SU3 Lie algebra, for example, and this occurs across the board, these matrices have nice patterns. They're aware of this, of course, and they use it. But the kind of nice patterns that these have is very close to the sort of patterns that I've been interested in a while algebraically, and that we keep bumping into when Roger and I and Sam and others are talking about Clifford algebras with each other. What you see is a matrix, and then you look at it and you see that except for its entries, it's a permutation matrix. If you were to take, for example, lambda 5 there in the middle, oh, well, that's not a good example. Well, yeah, these are good examples. It's almost a permutation matrix. In that you see that if you were to take lambda 1, for example, then it's a permutation matrix in its little 2x2 square at the top. But then the diagonal entry at the bottom would complete it as a permutation matrix, but it's got a 0. So you can look at each of these and see them as permutation matrices with perhaps a 0 entry in one of the permutation and matrix entries, and otherwise some scalar. And if you look at these, you would tend to fill in the right one, right? You see 2 of them and you need a third, and it has to be a permutation matrix. So you end up with a 0 in one of the entries. And you could write each of these as a diagonal matrix times a permutation matrix. And that's a nice way to think about the matrices, whose eigenvalues you want, and so on. So I'm interested in thinking about the matrices that way. So in other words, if it's 3x3 matrices, then I think of the 3 permutation matrices that fill out a 3x3 matrix. Here's a 3x3 matrix, and I put A's in the position of one permutation matrix, B's in the position of the other, and 1's in the identity position. And so I have the matrix A and the matrix B. And A and B and 1 form the cyclic group of order 3. And then I can have a diagonal matrix, which I'll write as ABC. And then I could write each of those Gelman matrices as a certain diagonal matrix times a permutation matrix, and possibly a combination of more than one. More than one because I was thinking of decomposing them the way the physics book did, into smaller matrices which were simpler. So this decomposition into T's and U's and V's and Y's corresponds to this one. And then I can write the T's and U's and V's, which are the ones that were being used in this particular handbook of doing the representation theory. Then each of these elemental ones is written as a diagonal times a certain permutation matrix. And there is the quark structure implicit. And to make it explicit, you got to go to one of these handbooks like this one and look at what they do. And they take those matrices and they look at their eigenvalue structure, and they look at what they do to vectors, raising and lowering them, and get them into a pattern. And then the pattern gives rise to the structure of the representation. And there's a story about that. So this is, again, unfinished, but I'm telling you about my particular way of trying to read those handbooks. This, by the way, is a nice handbook of gauge theory and group theory. It's got a nice chapter on the group theory, as do many physics books. You may have your own favorite. So this part of the project is to try to think about how some of the things I've told you about are related to the group theory. In particular, the 3-strand braids can be rewritten group theoretically as 3x3 matrices that are unitary, and so maybe matched into this group. But I haven't done it in a way that's satisfactory, so I won't show you anything. But that's a picture of the way this project seems to be working at the moment. And there are many questions, as I said. Relate 3-braid representations to SO3, explore the models and find out exactly what interactions are happening in them. That's combinatorics, which depends on the model, like what's happening with the paper folding in a Brin's model. How is it related to braiding? What is happening with that braiding? How are these models related to the representation theory of the unitary group? And what is the role of topology in fundamental physics? Lots of suggestions from across the history of it, and maybe more suggestions to come. That's the talk.
Oh, thanks, Lou. Great. Yeah, thank you. Are there any questions before I start asking questions? No. I was just, I mean, it was two things really. I mean, it's interesting that this idea of Kelvin has kind of like persisted in some, or sort of it died out and then came back zombie-like.
Yeah, it doesn't want to go away, does it?
I know. And I mean, what we have a situation where we cannot see these things really. So we try and get, I mean, this is what physics does, makes analogies of things with things we do know. But these ideas aren't really relevant unless some mathematics comes out of them, which is obviously, but which brings me to the point that a lot of your quaternions are like Hurewitz points in the quaternions. And Andy and I, we found solutions of the Yang-Baxter equation, the set theoretic Yang, which involve the Hurwitz points. Now, I've no idea.
What is the Hurwitz point?
Well, I'm gonna pass on that, but I know that if a half of 1 plus I plus j plus k is 1, and if I can change the signs of that, these are all, there's a Hurwitz ring, I think. But
I feel you imagining some algebra structure behind Lambeck.
Yeah,
that's what you're saying. Yeah, maybe.
So
yeah.
So
I'll look it up before.
Well, let me make another remark about the Yang-Baxter. We know that that in a funny way we ought to be thinking about not knots related to elementary particles, but knot invariants related to elementary particles, because a knot invariant can be constructed from an irreducible representation of something. Like an irreducible representation of SQ2 gives the Jones polynomial, and irreducible representations of SUN correspond to Humphrey polynomial specializations, right? So that's a funny thing that at that level it's not the knots but the knot invariants that are coming in. But that's a formal correspondence, and I don't know how to make something out of it. And the way it got made out of it for the non-invariant was to deform the Lie group, right? It wasn't SQ3 or SQ2. It was SU2Q, the quantum group, and then it had a Yang-Baxter solution in it, and that Yang-Baxter solution gave the Jones polynomial. So there's that story, and we understand that story a lot, but we don't understand how those irreps are related to the physics. Well, we don't, but if we had Gukov in here, he would tell us a lot about that we don't know. Yeah. I interrupted you. I'm sorry.
No. I'm glad you did, because I'm just shooting my mouth off. So about things I only half know.
Sometimes that's what happens to the speaker.
Yeah.
Yeah, right.
Are there any other comments? Well, this is difficult stuff. I don't know what the answer is or what the future would be, but I guess you don't either, Lou. All right, I'm not trying to speak on your behalf.
Well, of course, the point is the intent of this talk was certainly not to come to a conclusion. It was to raise these questions.
Okay. I think I have a volunteer for next week. Andy, are you able to give a talk next week?
I can talk next week. Yep.
Yeah, that would be great. Okay.
So it's be a description of a very simple problem of how to draw knot diagrams or knotoid diagrams, or smooth states of some kind of knot. And the talk will really be an advertisement for some software that I have that will draw pictures very conveniently and produce MetaPost code, so you can create nice, pretty pictures very quickly and easily, and just show how to manipulate it and those sort of things.
Question: Does your software also produce a list of 3D points for the knot, so it could be put into one of those energy programs like Knotplot?
No, not at the moment. It's a two-dimensional thing. It was originally designed to produce diagrams for knotoids, so it's all about planar diagrams. It has given rise to some interesting discussions with Roger about how to produce aesthetic two-dimensional diagrams, which is a non-trivial problem. I'm not thinking of talking about that next week. I think what the idea.
Did you ever look at Mr. Okiai's old program that does a two-dimensional? It's a two-dimensional drawing program, and then it produces a rather nice picture of the knot from your piecewise linear drawing.
No. So this is a program that uses circle packing to create a smooth picture of a knot. It was developed by reverse engineering some of the code in Knotscape or Knotplot. It's been knocking around for some 10 years. And it will enable you to draw arbitrary immersions, so you can draw virtual knots with any number of virtual crossings you like.
Very nice.
Or knotoids. You can draw knotoids with shortcuts. You can scale things, rotate things, all of the things you would expect to be able to do. More interestingly, and more.
Can you draw grid diagrams, Dienikov diagrams, things like that?
No, at the moment it's just for drawing. Well, so at the moment it can draw knot diagrams. It can draw smooth states. So you can just churn out all of the smooth states for a particular knot diagram. You can, or knotoid diagram. You can just recently I've added the capability to draw individual smooth states if you want simply to pick one of them. So you can say I want the state with these crossings smooth A, B, or whatever. I can now draw diagrams from Gauss codes or planar diagrams, which was the last thing that was added, which really motivated me talking to Roger about maybe just advertising this.
And if you make a drawing, it will produce a code for you from the drawing as well?
You start from the code and create the drawing.
But can you draw by hand and get the code from it?
No, it's a command line tool. It's a simple.
I see.
It was designed for churning out MetaPost code to put into papers and things of that nature.
I understand.
And
do you also allow input of PD code?
Yes.
Yeah.
Mm-hmm. Yeah. So that was the last thing I added. And the important thing with PD code or Gauss codes is that if you come up with a code for a virtual knot, then my program needs to be able to convert that into an immersion and put in the virtual crossings. So that's been added. That was a thing that was added just at the end of last year. So it's and it's an evolving thing.
That's very interesting. I'm looking forward to your talk. Yeah.
If somebody had some ideas about what will be added to make it more useful, then I'd be very happy to look at it. So anyway,
would you like to see Mr. Okiai's program in operation? I can show it to you right now. I'll just share a screen for a moment.
Yeah, sure.
It's a very old program. You've now gone back in time Okay, so oops. Oh, sorry. Let's make it alternating. Okay. So you make a PL drawing like that, and then it draws you a better version.
Sort of better. That's not very precise.
So
yeah.
no, not super good, but not bad, right? And and then you can compute an invariant, and it has a list of standard polynomials from that time, and so that's what OKIs look like.
Yeah.
And I still use it. That's a nice program, but it only operates in this historic environment.
Yeah.
But the thing is, Lou, is that you've got a human input into that. You see, if you've got a diagram on the board, on the blackboard, say, you can within minutes write down a Gauss code. It's easy, right?
Oh, I have no problem with starting with a diagram and writing a code and giving it to a computer.
Yeah, anybody can.
Yeah, I do that all the time. Yeah.
But if you say, you come out from behind a curtain and say, aha, I have this code, now draw me the knot. That's still okay if you're a human being, because you put the crossings on the board any way you like, and you join them up according to the code. You now tell a computer to do that.
Oh, I'm aware of it. In fact, I'm trying to think now off and on, but not very. I want to do the following. If you're doing, Andrew probably is thinking about this. If you have a nautoid and it's a planar nautoid, then you have the loop bracket. You have Turiev's idea of considering the way the state loops surround the long piece. And if you have the long state is surrounded by a loop, then that's a non-trivial thing. And so you get new variables corresponding to loops, numbers of loops surrounding the long loop, the long state. And so you want the computer program to find those. So you need to know the cell structure of the diagram. You can't just work with the code of it, the bare code of it. So yeah, that's in the same category as how do you draw it. Only you need it just to get the invariant.
Send me a reference to that. It's not something I've looked at. I've seen various comments about some of Turiev's work on nautoids, and these extra loops in some of your papers. But if there's a particular reference, I'd like to just see if there's something I could do easily with that, because it's not that difficult to come up with a cell
probably the simplest thing would be I could write you a one-page description of that invariant.
Do that. Yeah.
Well,
yeah, it may well be that some of the code that I've got is a step along the way to doing what you do.
A code that will draw a picture of the knot from what code you give it would probably also be able to find these configurations.
Yeah, because the drawing algorithm that I use is based on an understanding of the underlying immersion. You have to understand what the overall diagram looks like, and you need a cell decomposition effectively of that underlying immersion on a two-sphere, which is one of the things that can sometimes hamper you. But so the drawing is effectively on a two-sphere. So sometimes you have to sort of choose where you want the point of infinity to be regarded. So, but I'll put something together during the week, Roger, and then just sort of explain where we are with it, because this is something that Roger and I have used in various papers for I don't know, some years. It's been around for a little while.
Sure. Yeah. I mean, it's remarkable how such a trivial sounding sort of idea is so difficult to implement, you know. But,
yeah, the challenge comes when, and I'll see if I can show some examples of this next week, is that some codes, if you try and draw them with a particular algorithm, end up with very congested diagrams. So you end up with some sort of entanglement that you can't really see, not a quantum entanglement, a physical entanglement you can't really see. It's just closely knotted. And the challenge is how to avoid that generically in all cases. And
sure,
we've failed to find a solution to that. So.
Andrew, could you send me an email to lucow@gmail.com? That way I have your email address. Sure. I don't see it on my mailer, so then it's easy for me to send you something.
Sure, will do.
Good. So, interesting talk, and I look forward to next week's talk. Thanks again, Lou.
Yeah, thanks, Lou.
Okay, thank you.
We'll see you later. Yeah.
See you next week.
So I'll stop.
I'll see you in an hour.
Yeah, sure. But I need to stop this somehow.